Welcome. In this video, we are going to discuss about the fourth layer of the Open Systems Interconnection model, which is the transport layer. The transport layer is responsible for providing end-to-end communication between applications. We'll explore the protocols and mechanisms it uses for reliable data delivery. Here is an overview of the transport layer. The key functions of the transport layer include end-to-end communication between applications, ensuring that data reaches the correct destination application. It handles segmentation and reassembly of data, dividing large chunks of data into smaller segments for transmission and reassembling them at the receiving end. It provides connection-oriented transmission control protocol and connectionless user Datagram Protocol services, offering different approaches to data delivery. Flow control and congestion management are also handled here, preventing one host from overwhelming another with data. Finally, it is responsible for error detection and recovery, ensuring data integrity. Now let's compare Transmission Control Protocol and User Datagram Protocol. Transmission Control Protocol is a connection-oriented protocol, establishing a connection before transmitting data. It provides reliable data delivery with acknowledgements, ensuring that packets reach their destination. It also has flow control and congestion management mechanisms to prevent network congestion. Transmission Control Protocol guarantees ordered packet delivery. It also provides error detection and retransmission capabilities. Some common use cases for Transmission Control Protocol include web browsing using Hypertext Transfer Protocol or Hypertext Transfer Protocol Secure, email using Simple Mail Transfer Protocol and Internet Message Access Protocol, file transfer using File Transfer Protocol, and remote access using Secure Shell. User Datagram Protocol, on the other hand, is a connectionless protocol. It does not guarantee delivery or ordering of packets. It has minimal overhead as it does not require handshaking. It is faster with lower latency due to its simplicity. It also provides basic error detection without recovery mechanisms. Common use cases for User Datagram Protocol include video streaming, voice over Internet Protocol calls, online gaming, and domain name system lookups. Transmission Control Protocol connection establishment happens with a three-way handshake. This is how it works. First, the client sends a synchronized packet with a sequence number, indicated by X, to initiate the connection. Second, the server responds with a synchronized acknowledgement packet, acknowledging the client's sequence number as X+1, and sending its own sequence number, indicated by Y. Finally, the client acknowledges the server's sequence number as Y+1. The connection is now established and ready for data transfer. Let's take a look at the structure of a Transmission Control Protocol header. First, we have the source port, which is 16 bits long, identifying the sending application. Then we have the destination port, which is 16 bits long as well, identifying the receiving application. The sequence number is 32 bits long, indicating the position of data in the overall message stream. The acknowledgement number is also 32 bits long, indicating the next expected sequence number. Next, we have data offset, which is 4 bits, followed by a 6-bit reserve section. We have 6 bits for flags such as synchronize, acknowledge, finish, reset, push, and urgent. The window size is 16 bits long, used for flow control, representing the bytes the receiver can accept. Checksum is 16 bits long, and is used for error detection for both the header and the data. Finally, urgent pointer is 16 bits. Now, let's move on to the structure of a User Datagram Protocol header. A User Datagram Protocol header consists of a source port, a destination port, a length, and a checksum. The source port is 16 bits long and identifies the sending application, though it is optional. The destination port is 16 bits long and identifies the receiving application. The length is 16 bits, representing the size of the User Datagram Protocol header, and the data in bytes. Lastly, checksum is 16 bits and provides optional error detection for the header and data. A Transmission Control Protocol header is 20 to 60 bytes, and the user Datagram Protocol header is 8 bytes. Now, let's see how Transmission Control Protocol Flow Control happens, managing the data transfer rate. Flow control prevents a sender from overwhelming a receiver by regulating the rate of data transmission. The receiver advertises its available buffer space using the window size field in the Transmission Control Protocol header. Key concepts for Transmission Control Protocol Flow Control include the receiver window, also called receive window. This is the available buffer space. A zero window means the receiver buffer is full, so the sender must pause. A window update is when the receiver notifies the sender when space is available. A sliding window adjusts dynamically during transmission. As an example, we can consider a client as a sender and a server as a receiver. Now, let's understand Transmission Control Protocol Congestion Control and how it prevents network overload. Congestion control prevents network overload by adjusting the sender's transmission rate based on network conditions. Unlike flow control, which protects the receiver, congestion control protects the network itself. Key algorithms include slow start, where the window exponentially increases until it hits the threshold. Congestion avoidance linearly increases the window after the threshold. Fast retransmit resends packets on duplicate acknowledgement, and fast recovery avoids slow start after packet loss. Transport layer ports are used for addressing applications with port numbers. Port numbers identify specific applications or services on a host. They allow multiple applications to use network resources simultaneously on the same device. Each transmission control protocol, or user datagram protocol connection, is uniquely identified by 4 values. These are the source Internet Protocol address, the source port number, the destination Internet Protocol address, and the destination port number. There are 3 port number ranges: well-known ports, which range from 0 to 1023, registered ports, which range from 1024 to 49151, and dynamic or private ports, which range from 49152 to 65535. Examples of common well-known ports are Hypertext Transfer Protocol on port 80, Hypertext Transfer Protocol Secure on port 443, Simple Mail Transfer Protocol on port 25, File Transfer Protocol on port 21, Secure Shell on port 22, Domain Name System on port 53, Network Time Protocol on port 123, and Session Initiation Protocol on port 5060. To summarize, the transport layer provides end-to-end communication between applications running on different hosts. Transmission Control Protocol offers reliable, connection-oriented service with flow and congestion control. User Datagram Protocol provides lightweight, connectionless service with minimal overhead. Port numbers enable multiplexing and demultiplexing of data to and from multiple applications. Transport layer protocols handle segmentation, reassembly, and error detection. The next layer we will be studying is the network layer, which handles routing of packets between different networks, addressing hosts with Internet Protocol addresses, and determining the best path for data to travel across interconnected networks. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.